all, thank you for inviting me to this summer school, and also hello to everybody, to all the assistants. So what I'm going to do is to talk about in this talk is to talk about a very hot topic right now in deep learning, which is computationally efficient deep neural networks. Okay. So this is the outline of the presentation. So I will start with some introduction and motivation, where I will try to introduce the problem and also try to convince you why this topic is so important right now in deep learning, and it will be much more important in the following years. And also, and after that, what I will do is to introduce you some of the frameworks, of the approaches that we have already available to build these computationally efficient deep networks. So this is not going to be an extensive review of all these methods. So I'm going to just introduce the basic notions for all these frameworks, and I'm going to illustrate the basic ideas with some papers that maybe they are not the state of the art right now, but they will be useful to understand all the basic concepts. And I will finish with a summary of all the things that we have seen. So what I'm going to do is to, so typically we'll do a small break every 5-10 minutes, so probably 10 minutes. And so I will let you time, so if you can have, if you have any question, okay? So let's start with the introduction and the motivation for this topic. So, so in the last years, we have witnessed the explosion of deep learning, in the sense that deep neural networks have become the standard tools to solve many machine learning problems. And basically, the reason for that, and I think this was mentioned by Xavier Giraud in the first presentation, and not the main reason, but probably one of the most important reasons, is the fact that nowadays we have much more computational power, so that we can train these deep neural networks that we were not able to train before, because we didn't have this kind of super powerful cluster of GPUs or TPUs or this kind of specialized hardware for this kind of models, right? And actually, we can see clearly this in this chart. So, so in this chart, what I'm showing is the performance of standard convolutional neural networks, okay, on ImageNet. So in the y-axis, you see the performance, the accuracy, and the x-axis, what we see is the number of operations required to process a single input image of ImageNet by these different networks. And also the size of each of the points here represents the number of parameters of these models. Okay, so you can get an idea of the computational complexity of different networks by looking at this graph. And what we can clearly see is that usually there is a high correlation between the computational complexity of the networks that we use and the accuracy, the final accuracy that we obtain. And this not only happens for ImageNet, but it also happens for many different problems. And this is true if we have enough training data, right? So actually, to go more in detail, if we analyze, for example, the family, some different networks belonging to the family of ResNet. So here we have ResNet 18, ResNet 34, ResNet 101. This number simply means the number of layers for each of the networks. We can see that when we add more layers to the network, so that when we add more computational complexity to the network, the accuracy typically improves, right? So this is what we have learned in the last years, and it's quite nice. But the question is, okay, so if that holds, if you have enough training data, and the only thing you have to do is to solve a problem, it's just adding more parameters to the network, right? But but relying only on computational complexity has many drawbacks. Okay, and these drawbacks, I'm going to try to convince you that it's not a good idea to always rely on computational complexity, and that we need to develop efficient, and we need to start focusing on efficiency rather than on simply performance. Okay, so what is not a good idea to rely simply on computational power? So one of the reasons, probably the first two reasons will be quite obvious for you. One of the reasons is that when we deploy a neural network in a device, so the devices that we can deploy the network can have different kind of hardware, right? So it's not the same to deploy a model into, into a cluster of GPUs with a lot of computational power than deploying it into some devices like drones or smartphones or robots, because the hardware is much more limited, right? So the computational resources are lower in these cases. So if we train a very big model in a GPU cluster, then we will not be able to run this model into this kind of devices, and there are many implications that we need to do this. Okay. So the second reason is that even in the case that we have enough computational power, so for many applications, we require low latency prediction. So we require that our network takes just a small fraction of time to produce outputs from the inputs. And for example, in cases like assistive robotics or online surveillance or autonomous driving, we need real-time performance. So because we need, in many situations, we need to take decisions very fast, right? And if we deploy a very big model into a device, so we will not be able to achieve this real-time performance. Okay, so these are the most obvious situations, right? But there are other ones that maybe are not known by you, or maybe you don't really understand the consequences of it. So the third reason that I wanted to talk about is about sustainability. Okay, so big models. So when you deploy a network into a device, this device requires energy, and energy is not free. Energy needs to be produced, and typically this is produced. Let's say the processes that allow us to produce electrical energy and also produce carbon emissions, which has a negative impact on the climate change, the global warming, and all this stuff, right? So if in few years you have millions of devices and millions and thousands of companies training their own models and millions of devices running deep learning models, we have to take care about what is the impact on the climate, on the sustainability for this technology, right? And actually, in this paper I mentioned here, they estimated what was the required carbon emissions. So what were the required carbon emissions to train one of the, let's say, the most powerful state-of-the-art model for natural language processing. Okay, so this a transformer, a very big transformer that I think in some presentation before it was introduced, and also so all the experiments that were needed to tune all the hyperparameters and so on for this kind of model. And what they found is that to train that model in the paper where it was introduced, you need 5 times, so you produce 5 times the carbon emissions that a single car produced in its entire life. So you can imagine that if the learning technology becomes even more and more popular, you can imagine that we cannot have thousands of companies training this kind of models, because it will have a really, really negative impact into our climate and for the global warming, right? But maybe you don't care about climate change or global warming. It will happen because, I don't know, you plan to move to the Arctic at some point, but probably what you care about is about money, okay? And energy, so producing energy also produce carbon emissions, but it's important to take into account it costs money. So kilowatts per hour costs money. And so in the same paper, they estimated what is the cost of training a state-of-the-art natural language processing model, GPT-2, and they estimated that it costs around $10,000 to $40,000 to train this model. And this seems quite high, but actually, if we take a look to these other models that use neural architecture surgery training, that is something I'm going to talk about later, you see that the numbers are even much more impressive. So you can imagine that not everybody, actually just probably 4 companies in the world can afford to train a model of this size. And this is basically because all these models are extremely computationally expensive. And to train them, you need a lot of computational power and a lot of energy. So, and this last drawback that I mentioned, it's also related with something that we have also to take into account, and that we also need to take care with, is the democratization of deep learning. Okay, so probably in few years deep learning will be everywhere. So we will always have, like, for most of the applications in many industries, we will have a deep learning model running. And what we need to ensure, if that is the future, what we need to ensure is that most of people can have access to this technology. So not only like big companies, but also small companies, startups, researchers belonging to small groups, and so on. And that's really, really important for many reasons, because, for example, McKinsey and Company, in a report in 2018, they estimated that by 2030, companies that fully absorb AI could double their cash flow, while companies that don't could see a 20% decline. So this basically means that companies that absorb AI, that don't absorb AI, will probably disappear, right? And if we have a look to the words of Joshua Bencho in Financial Times, in an interview in Financial Times, where he said that basically currently the power, so the computational power, are all concentrated in the hands of the few companies. So this, obviously, if we don't start looking at efficiency of deep learning, we are going to a future where only 2-3 companies in the world will have access to this technology, okay? And when I say access, I mean developing products with access, okay? We will have access as users, but the people who will develop this technology will be just a couple of 3 companies, okay? So, okay, so I hope I motivated why do we cannot rely only on computational power for deep learning. And now I'm going to explain what are the main frameworks that we have already available to build computationally efficient deep neural networks. But before that, I want to just do a brief break, a brief parenthesis, to explain how we typically measure efficiency in deep neural networks, in case you are interested in this topic and you want to read some papers about it. So when we think about efficiency, we can obviously think of things like the latency, so the amount of time we need to process an input, the memory required to store the model, for example, and the energy consumed, right? And but the point is that this kind of metrics, so you will not usually see this kind of metrics in research papers because they are extremely depending on the hardware and on the implementation, right? So depending on the hardware, the latency will completely change, and also implementation, the memory, etc., right? And this makes these metrics not suitable for comparing different efficient deep neural networks. So what people usually do is to compare efficiency in terms of 2 metrics. One is the number of model parameters, which is it's quite related with the memory, right? Because it's the number, because to store the parameters of the model, you need some memory. And also with and the other metric is the flop. So it's the number of floating point operations that you will run in the device where you have deployed your neural network, required to process a single example. So these 2 metrics are, and these flops are completely correlated also with the latency. In most cases, not always the case, but most of the cases is quite correlated with the latency. So usually in the papers, in research, what we use is these 2 metrics to make them independently from the hardware and the implementation. So yeah, so I'm going to start now with the first framework that we have available to build this computationally efficient deep network. So if anybody have any question, otherwise I'll just continue. Okay, good. So anyway, if we have time at the end, you can ask about anything. So I think it's fine. So the first approach, the first framework that we have for developing computationally efficient deep networks is what we can call manual architecture engineering. So what is the idea behind it? So usually when so assume that we have a convolutional neural network. Sorry, but I didn't mention that most of the examples will be about convolutional neural networks, basically for 2 reasons. One reason because it's my area of expertise, computer vision, so it's what we're more familiar with. But the second reason, which is more important, is that most of the research in this computationally efficient deep networks topic usually are based on these convolutional neural networks. Okay. So imagine we have a convolutional neural network. This is the AlexNet, And during training, we just optimize the parameters of this network, right? But the point is that this model has some hyperparameters which define its architectures, right? So for example, we have the number of layers that we use, the kernel size of the convolutions, we have also the number of input and output channels, and all these hyperparameters are fixed during training, so they are not optimized, but they define what is the computational complexity of this model. So one of the things that we can simply do to reduce, to make more efficient a network is to modify these hyperparameters, right? So for example, one thing that we can do is simply reduce the number of layers. It's very simple. We simply remove one of these layers and that's it. And actually, when you see papers proposing a novel network architecture like ResNet or DenseNet, so typically you have experiments where they test different variants of these models by adding or reducing the number of layers to show that these kind of models can be implemented efficiently or more computationally or in a more computationally expensive manner. Okay, typically what we observe is that the more layers we add, the more computational complexity, but also better the performance. That is what we actually expect. But apart from reducing layers, there are other hyperparameters that we can fine-tune, right? So we have the number of input and output neurons in each channel, in each layer, or input and output channels in the case of convolutional neural networks. We have also the kernel size of the convolutional blocks, because these kernel size, so higher kernel sizes, implies more computation when we are doing the convolutions, right? And more parameters, obviously. And so we can modify this. And actually, for example, is QuizNet, which is a paper from 2016, quite old today, but it was one of the first papers that focused on computationally efficient big networks. They took the AlexNet network, so the base network from AlexNet, and what they did is to reduce the kernel sizes of the convolutions to 1x1 and 3x3 convolutions, and they reduced it also the number of input and output channels for the 3x3 convolutions, which are typically the most expensive ones in terms of operations and parameters. And what they found is that if you do this, you can obtain a very similar performance to the original AlexNet, but using 50 times less parameters, which is a lot. So in terms of memory, it's a lot. So actually, by modifying correctly these hyperparameters of a network, we can obtain a model that achieves a similar performance, but much more efficient. Okay. So other things that we can do, well, we can remove fully connected layers, which usually have a lot of parameters. And for that, we can use the notion of global average pooling, which so basically in the convolutional neural network, after the last feature map, you have a fully connected layer. And this fully connected layer, it's connected to all the inputs. So these feature maps in the last layer are flattened, and then a fully connected is used to obtain the final output. But what we can do instead of this is to remove all these fully connected layers, so all the parameters here, and simply compute the output of each neuron by averaging the values in each of the feature maps independently. So this is what is called global average pooling. It's quite useful, and it can reduce significantly the number of parameters for the last layers of the network. So yeah, apart from changing hyperparameters in a network, other approaches have a focus on designing more efficient convolutional blocks. Okay, and actually one of the most popular efficient convolutional block used out there is group convolution. So the idea of group convolution is the following. So in a standard convolution, all the input channels are connected to all the output channels on a network. But in group convolutions, what we can do is basically to make different subsets of input and output channels and connect them, and remove the connections between them. So for example, we have, so in this case, we have 6 input channels and 6 output channels. So the first 3 will be connected to the first 3 output channels, and the second 3 input channels will be connected to the second 3 output channels. And basically, because we have made 2 groups, 2 subsets of this input and output channels, so the number of groups is equal to 2. But we can do the same for any number of groups, right? So we can make 3 groups, for example, here, or we can make 6 groups in this case, which actually it's the same number of input and output channels. So this means that only one input channel will be connected to only one output channel. And so this makes sense, because if we take into consideration what is the computational complexity of a standard convolution, which is, so then, for example, for the number of parameters, we have C out by C in, where C out is the number of output channels, C in is the number of input channels, and K by K is the kernel size of the convolution. We see that with group convolutions, we can obtain a reduction in the number of parameters by dividing this number by G, where G is the number of groups that we are creating. And similarly for the flops, for the number of operations that we need to make a convolution is the same, but we only take into consideration W by H, which is the resolution of these input channels that you need to where you need to compute the convolution. Okay. So this idea was implemented, for example, by ResNext, which is a variant of ResNet, where simply the usual convolutional block of ResNet is replaced by a convolutional block with by using group convolutions with 32 groups. Okay, so and this reduces a lot the computational power, and actually here we see that so the yellow line is the ResNext, so the efficient version with group convolutions, and the red line is the original ResNet, and you can see that you can have for the same number of parameters or flops here, you can see a much better performance in terms of accuracy error. Okay. This idea was also used, so if you take this idea and go to the extreme of this idea, you will have a number of groups equal to the number of input channels, and this was used for to create the depth-wise separable convolutions that are defined in the MobileNet networks. Okay, so MobileNet, there are many versions of it. You have MobileNet version 1, version 2, version 3, and soon version 50. And so it's a very popular family of networks that that is very efficient, and you can use it if you have any problem where you want an efficient architecture. Okay, and in the core of these networks, they use the concept of depth-wise separable convolutions, which is the idea that instead of using a 3x3 convolution, what we're going to do is a composition. We are going to replace the 3x3 convolution by a composition of a 1x1 convolution, okay, which is very, very efficient. It's much more efficient than 3x3. It's 9 times more efficient. And then we are going to apply a 3x3 group convolution with groups equal to the input channels. And these operations, so these operations concatenated, are much more efficient than a standard 3x3 convolution in terms of parameters and in terms of flops. So yeah, so here is just a graph showing that with MobileNet version 1, actually this is a quite old architecture, so now you have MobileNet version 3, which is extremely much more efficient. But here in MobileNet version 1, they already were, with using this idea of depth-wise separable convolution, they were already able to get much better accuracy efficiency trades-off than other standard architectures like AlexNet or GoogleNet or BGG that were standard at the time that MobileNet was published. So yeah, so okay, so manual architectural engineering, but there are other kind of approaches that have used this kind of framework. So for example, we have people who have tried to use parallel convolutions at different resolutions, where the different resolutions typically have so requires less computational power because you have less you have less input because you have less resolution. You also have people working on efficient convolutional blocks for specific problems like segmentation, like semantic segmentation, where dilated convolutions are quite efficient. And also other people who have tried to, for example, to find what is the optimal combination of network width, depth, and resolution that gives you the higher accuracy and at the same time give you the most efficient architecture, network architecture. So yeah, so the general idea, so manual architecture search, we can modify hyperparameters of already existing network architectures, or use efficient or design efficient convolutional blocks. This is a straightforward solution. It's very easy to implement, but it has a drawback, right? So the drawback is that the number of hyperparameters that we can modify is extremely large. So we have a very large architecture space to explore, and we have to do this manually. And this is not an easy task because this process is typically guided by trial and error. And the reason is that given an architecture and a given hyperparameter, like let's say the number of layers, it's very difficult to predict what will be the accuracy drop if we change that hyperparameter to a certain value. So what we typically need to do is to just get the network, reduce the number of layers, and train the network and see what happens, right? And this is very costly, and it's not the best idea in most of the cases. Okay. So yeah, so I think this is everything for the first framework. If anybody has questions, otherwise I just continue. Okay. So I just continue. So now I'm going to talk about neural architecture search. Okay. So before I told you that we have the option to modify hyperparameters to find more efficient networks, right? But as I told you, doing this by hand is extremely costly. So the idea of neural architecture search is to use this idea, but automatically. So do this search in the architecture space automatically, right? So that we don't need to do it manually. So basically, let me just formalize a bit, just one or two formulas. What is the main idea? So basically, in standard network optimization, we have a training set and an architecture which will be fixed in training and some learnable parameters, let's say the weights of the network, the biases, and so on. And what we do is to optimize these parameters with respect to using a loss function over the training set. And this architecture here, as you see, is completely fixed, right? So we have to fix it before training. So the idea of neural architecture search is to say, okay, so what we can do is instead of just optimizing the parameters of the network, what I would like to do is also optimize the architecture of the network, optimize all these hyperparameters which determine what is the computational complexity and the accuracy of my final model. Typically, this is done by defining another validation set and performing some kind of an optimization, an alternate optimization like this, where we optimize the architecture by using this validation set, using a loss function, and we also, so alternatively, and then we optimize the parameters of the model in another training set. Okay, so this is usually what's on in so the pipeline of training neural architecture search methods. But why is this important when we are designing computationally efficient networks? Well, because into this optimization that I show you, what we can do is to add constraints that somehow limits what is the complexity of the architecture that we are optimizing. So here I can just add a constraint. Let's say the cost of my architecture should be less than some constant, and this cost can be measured in terms of whatever you want, the parameters, the flops, the latency, whatever you want, and you can introduce this constraint into the optimization problem so that when you optimize all the architecture and the parameters, you get a network that is exactly is as efficient as you want it and also has the optimal, so the highest accuracy possible. But obviously this has this is not a difficult thing, so optimizing architecture is not an easy thing, sorry, because there are questions such as how you can define an architecture space, so what are the possible architectures that you will consider to optimize, how you will optimize the architecture, because usually it's a discrete, so the space of architecture is a discrete space, so the number of layers is discrete, it's not continuous. The number of input channels is discrete, it's not continuous. The connectivity is discrete. So how you can optimize this, and also how you can incorporate this computational constraints. So for this purpose, we can use either controller-based or one-shot methods in neural architecture search. So I'm going to just briefly introduce the basic ideas by explaining them using concrete examples of different methods that were proposed 2 years ago. Okay, so the idea of controller-based neural architecture search is the following. So we have in controller-based neural architecture search, we have different components: the controller, the training, and also the updater of the controller. So I will explain now what is the main idea behind all these components. So what is the controller? So the controller will be a parametric model, let's say, for example, neural network or recurrent neural network, that will define a probability distribution over the architectures in the search space. So in our search space, we will have like thousands of possible choices for the hyperparameters of the architectures, and we can define a distribution over all these kind of hyperparameters, and so we can define a distribution over all the architectures that we want to optimize. And also, it's important to have a probability distribution because we will need to sample architectures from this distribution. Okay, and why is that? Because the second component is the trainer. So what will do the trainer is to get a component, to get architectures that are sampled by the controller here. And we will take these models and we will train a model with that architecture into the training set or validation set or whatever you want. So you will get this architecture, you will fix this architecture, and you will do standard training over the weights of the network. And finally, we have the controller updater, which basically will take these trained models with the trainer and the fixed architecture sampled by the controller, and we'll see what is the accuracy in a validation set, and also what is the computational cost, let's say the latency, the number of flops, parameters, and whatever we are interested. To understand much better this idea, I'm going to explain this paper just briefly, Endlessness, which is a quite relevant paper published in 2018. And in this paper, the first thing they did is to define the search space, right? So what is the space of architecture that we are considering during our optimization? So what they said is, okay, so we're going to define the search space as following. So we are use a network with a predefined number of B blocks. This B blocks is a hyperparameter that will not change during optimization. Okay, let's say 7 blocks. And each block will contain n number of layers whose architecture will be optimized. So each of these blocks here will contain n layers, and we will optimize not only the number of layers that are in this block, but also what is the connectivity and the hyperparameters that define these layers. Okay. So how we can, so what is the kind of layers that we are considering? Well, so each layer will be a sequences of possible of tokens that will define possible operations that we can apply to the layer. For example, we can imagine that we have T operations and we apply T convolutions, and these tokens will define, for example, this sequence will define what is the kind of convolution that we will use. For example, a depthwise convolution or a convolution. What is the kernel size? The squeeze excitation ratio, okay, whatever, it's not important. Or if we, instead of convolutions, we use identity or pooling operations, what is the filter size and the number of layers the number of operations per layer, right? So, this is the kind of search space we are considering for each of the layers. And basically, our controller will be a recurrent neural network that will model a distribution over these sequences here, defining what are the operations that the layer can have, right? So it will have we will have a distribution over different sequences of these tokens, and each sequence will define a single architecture for these layers. So with this recurrent neural network, we will be able to sample different layers and use it as the controller. So with these components, the Endlessness paper, what does is basically the following. So at each iteration, we sample a set of possible architectures with our RNN. And then what we do is to get these architectures and train in parallel a model for each sample architecture and evaluate the accuracy and the latency in the validation set. And finally, with this accuracy validation for a given architecture, what we do is to use reinforcement learning to update the controllers, so the parameters of this recurrent network, by maximizing a reward, taking into account what is the accuracy and the latency. So basically what we're doing is saying, okay, so give me this architecture, let me see how this architecture performs, and also what is the cost of the architecture, and if I'm happy with this architecture because the accuracy is good and the computational complexity is also good, I will update the controller so that I give more probability to this kind of architectures. Okay, so that is the basic idea. And yeah, there are many technical details that I'm just skipping, but this is the main idea. And the point is that with this kind of models, what we can do, so with this Endlessness, what we can do is to find actually very efficient convolutional blocks that maybe are not so intuitive and that probably we wouldn't find by manual search, but that they work extremely well. And actually here in this graph, we can see the performance of this Endlessness on ImageNet, and we can see that the performance is much better with the same computational efficiency than other models that are manually engineered, right? So yeah, so it seems that neural architecture search is a really good approach to solve our problem of finding computationally efficient deep neural networks. But well, so it achieves state-of-the-art results, but the problem is that the optimization process of the architectures is very computationally expensive. So typically it requires hundreds to thousands of GPU hours to do this kind of architecture search optimization. And the reason is very simple, is because each time we sample an architecture, we need to train a separate model and update the controller and do this iteratively, which means that if for example, a model on ImageNet takes like 3 days to compute in 8 GPUs, imagine what happened when you need to train thousands of these models to update our controller, right? So this kind of approach is only available for really big companies which want like to spend a lot of money, a lot of energy on finding optimal networks that then they will deploy at large scale. But there is another approach to do architecture search with this one-shot neural architecture search, that what it tries to do is to remove this controller and make the searching, the optimization process over the architecture space much more efficient. Okay, so what is the idea of one-shot neural architecture search? So the idea is that instead of having a controller that's sampling independently networks, what we are going to do is to define a super network, okay, which embeds all the possible architectures that we have in the search space. Okay, so if we have this, we can jointly optimize them by optimizing the super network. We are also optimizing at the same time all these small architectures that are embedded in it, and also we can include the computational constraints. So that then, when we have trained the super network, what we can do is to select the optimal architecture or the best architecture that is embedded into this super network. Okay, maybe now the idea is a little bit abstract and high level, but I will show you now more in detail how typically this is done. And for this, I'm going to talk about this paper, Proxima Nas, another very popular paper published in Clear 2018. And what in Proxima Nas, what they do is to define a network with n blocks. Okay, so this n is fixed. We will have a network with n blocks, and these blocks will form something. We will have this form more or less. Okay, so we will have some intermediate feature maps, and the connections between these feature maps will be different types of operations, convolutions, identities, or whatever. Okay, so we will see now what are the operations. And the point is that the connectivity and the number of blocks is fixed. What is not fixed is what is the operation that we apply at each feature map to obtain the second feature map here. Okay, and so this is what will determine what is the architecture of the network, right? Why is that? Because, for example, this is the possible operation that we will consider. So basically, we will have from 0 to 1, we can have either an identity, so no complexity, no computational complexity, just we don't need to do anything, or we can have max pooling, or we have depth convolutions, or whatever. So we can, with all these options, plugging one of these options to each of these red squares, we can have many different types of blocks, so many different types of architectures. So now what we're going to do is to define a separate network. So this separate network will be implemented in the following manner. So now what we will do is that the connections between these feature maps will be implemented by some parallel branches, where each branch, okay, will be one of these operations. Okay, so we will have, for each of these operations here, we will have a branch connected from the 0 to the 1 or the 0 to the 2 or whatever. And each one of them will have the different parameters, okay? And what we will do is that we will assign a probability to each of these edges, okay? So we will assign probability saying, okay, for this to go from 0 to 1, we have a high probability of use a 3-by-3 convolution or identity pooling or whatever. And what we're going to do is during training, we are going to use these convolutions, these probabilities, to sample different operations and also validate what is the accuracy with that particular sampling, so with that particular architecture produced by sampling these edges, these operations, and then we are going to optimize the parameters of these, the parameters of these operations, and also the probabilities that we have here. So if selecting this convolution 3-by-3, we get a very bad performance, this alpha, which determines probability of selecting this, will go lower. But if the accuracy is good, it will go higher, right? So this is the basic idea. And also, apart from minimizing a loss, taking into account the accuracy, we will also minimize the computational complexity. So the expected latency that we expect from sampling a given architecture. So from the expected latency, the expectation of the latency of all the architectures that are embedded into this super network according to these probabilities. And this latency is actually very easy to compute, because for each operation we can estimate what is the latency of applying this operation to the input to obtain the output. And so the expected latency for this block is basically the latency of these operations multiplied by the probability of being sampled. Okay, so we can easily add this constraint into the optimization process of these probabilities. So yeah, so this is the idea of Proxima Nas. And actually, the good thing about one-shot architecture search is that you can get similar performance to other architecture search based on controllers. Okay, so for example, here we see here you obtain a 74% with 79 milliseconds of latency, and in Proxima Nas you get 74.6 with the same latency. But what is important to see is that the cost in terms of GPU hours to explore the search space and optimize the architecture is much more bigger in the clients of Endlessness. So you see here 40,000 GPU hours, which is absolutely crazy. But with Proxima Nas or with one-shot architecture search, we can optimize architectures just using, for example, 200 GPU hours, which is much more feasible. It's still not affordable for everyone, but yeah, it's still much more feasible. And so yeah, so general idea of new architecture search, we want to find optimal and efficient architectures by automatically exploring a large architecture space. New architecture search nowadays produces state-of-the-art computational efficient architecture. So most of the computational efficient architectures that are being used right now were found by using new architecture search. But this is an approach that is not affordable for everyone, because even in the case of one-shot architecture search, the optimization process generally requires a lot of computational resources and GPU hours. And trust me that it's not affordable for everyone. And so yeah, so I'm going to move to another framework now. Probably I will not have time to cover the last one, but it's fine. But if you have questions, just ask me. Questions? Okay. So now I'm going to talk about network compression. Okay, which is another way to build these computational efficient deep neural networks. So the idea of network compression is that given an overparameterized model, we would like to obtain a more efficient version of it without sacrificing performance. So the idea is very easy. We have a hyperparameterized model, a big model, and we want to train a version of it that is much more efficient, but trying to not lose a lot of performance. And basically, there are many approaches to do this. Probably one of the most popular ones is network pruning, where we can differentiate between online and offline network pruning, and network escalation. Okay, so I'm gonna explain what is the main idea behind this approach. So in network pruning, the idea is very intuitive. So given a network with some connectivities and some neurons, we want to remove a subset of weights or neurons in this network to reduce the number of parameters and operations, and that the output of this network is similar to this, let's say, pruned network. Okay, so basically what we expect is that there will be some weights here and some neurons that are irrelevant for the network, that are never used, so that don't have any impact on the final result. So this means that probably we can just remove them and we will obtain the same output. And therefore we will reduce the computational complexity and the number of parameters. So basically, from a more formal point of view, what pruning methods are is the following. We have an overparameterized network, okay, F, with some parameters W, which you can think they are the major weights, so with these edges here, connecting neurons. And what we want to do is to, when we train a model, we want to minimize, so optimize the parameters by minimizing a loss function over a training set. But what we also want to do is to find a binary mask M, which will put some of these weights, a certain percentage of these weights, to 0. Okay, because this means that these weights will not be used, so that we will be able to freely remove it, because we know that they will have no impact because they are 0, and you get the idea. And also, this binary mask should fulfill some constraints according to our computational constraints, right? So we can say that this binary mask should have a certain percentage of weight set to 0 or set to 1, and this will modify the computational complexity of this final model. So this is easy to understand. The question is how we optimize, or how we address this optimization problem. There are many ways to do it. Maybe I'm going to talk now. Yeah, I'm going to talk now about offline network pruning. Okay, so we can do this offline or online. I'm going to explain now the difference. So in offline network pruning, basically the idea is that we start with a pre-trained network, okay, and that has been pre-trained, so it has a good accuracy. It's over-parameterized and it has a good accuracy. And then what we do is to evaluate somehow what is the importance of the neurons or the weights in the network. And then, taking into account this importance, we will remove the least important neurons according to the score that we have computed in the previous step. And finally, we will remove, so we will set this binary mask to 0 for all the non-important weights. And then, in order to recover a little bit the performance of the original overparameterized model, we will fine-tune again our model, taking into account this binary mask, so that the pruned model can have a similar performance than the overparameterized model. So yeah, so this is the idea. This is the optimization process. So, but the question is how we can evaluate the importance of the neurons, right? So there are, I don't know, hundreds of different approaches to evaluate the importance of neurons. But the most intuitive ones, actually the ones that actually work quite well, to be honest, and they are not really sophisticated. One of the things that it's typically done is just getting what the magnitude of the weight. So we will assume that if a weight, so a connection between a neuron and another neuron, it's low, it means that we can safely remove it, because it will not have a lot of impact into the final output. Okay. So this works pretty well, to be honest. So it's very stupid, but it works pretty well. There are some theoretical explanations for that, but are much more sophisticated. And then what we can do also is to use, instead of these weights, to use the weight derivatives. Okay, so basically to compute what is the derivative of the loss over our training set or validation set with respect to each of the parameters in the network, because this derivative, intuitively, it's giving us information about how much the output of our network will change if we change these parameters. So it's quite reasonable to think that this can be used as an important score for the weight and to know if we can freely remove it from the network or not. So yeah, this is the idea of line network pruning. But also we have online network pruning. So in offline network pruning, we start from a pre-trained network and we just remove weights. But the other thing you can do is to optimize this binary mask, removing weights, and at the same time optimize the parameters. So what I mean is that we just start this optimization instead with a pre-trained network. We start with a randomly initialized network. And again, there are many approaches for that, but the most intuitive one is it just adds some constraints into the magnitudes, into the weights directly. So for example, if you use the L norm, the L0 norm over the weights, you know that this, if you use a regularization taking into account the L0 norm over the weights, you know that these weights will be sparse by definition. So you will get a lot of zeros in these W's. So you will get an efficient network where you will be able to remove a lot of connections between the neurons. So yeah, so this idea of pruning has been applied also to structured pruning in convolutional neural networks. So instead of just removing individual weights, what we can do is to remove superstructures in convolutional neural networks, for example, feature channels or convolution or groups inside group convolutions, so branches, right? Or even entire layers in residual neural networks. And you can apply the same ideas as before, but just applying this pruning to superstructures into of the convolutional neural networks. And yeah, and finally, so apart from pruning, another way to compress neural networks is using network distillation. And so the idea of network distillation is that similar to offline pruning, we start with an overparameterized network that has a very good performance, but it's computationally expensive. And we will call it the teacher network. Okay? So why? You will see why now. Because now we will have what we will call the student network, which is a non-trained model, which is much more efficient than the teacher network, and that we want to train for a particular dataset. The idea is that we will use the teacher network to, so instead of simply optimizing the student network with our training data and that's it, we will want to use the teacher network to somehow provide more information, to transfer the knowledge from the teacher network to the student network, so that the student network somehow gets better accuracy in the training set by exploiting this kind of knowledge that this teacher network provides. So this is so to do this, it's very simple. So what we do is during training, we will optimize the student network by using a standard. Let's say we have a classification problem, so we have a minimize the standard cross entropy loss using the ground truth labels here. This is the output of our network. And additionally, this is what is called the distillation loss, which is the loss that will somehow transfer the knowledge from the teacher network to the student network. And the idea is that we will use again a cross entropy loss with the output of the student network, but we will compare this output of the student network to the some kind of soft labels generated by the teacher network. These soft labels, you can imagine, is simply the probabilities for all the classes. So you will compare the probabilities for the output probabilities for a given class, for a given example of the student network, to the ones provided by the teacher network. And if you do this, actually, you can get, so typically what you observe is that the student network, it's better, so you obtain better student network than in the case that you simply train the student network without this distillation loss. But not only this, also typically the student network converges much faster, okay? So you, at this point, there's one thing here I want to mention. I've never understood why this works. So I tried to find theoretical papers explaining why this works. I never found it. And there are some papers trying with some yeah, a bit hand-wavy explanations. So don't. So if you find the answer to this question, I will be very happy to understand it. But the point is, so the most important thing in this moment, I think, is that it really works. So if you do this, it really works. And this idea of distillation has been also extended to network of distillation, where the point is that perhaps, so in network of distillation, we don't have anymore this notion of teacher and student network, but we have just 2 networks or 3 networks or 4 networks, and all of them learn from each other. So we are going to train them together, and we're going to apply the distillation laws in both directions. So these networks will somehow learn from this one, and this network learn from this one. And again, this works, and I have so there's no theoretical explanation for that yet. So for me, it's quite interesting. It's quite interesting question. Whatever. So let's put some results, and I'm telling you that this works. It actually works. So let's see some results. So this is Cypher 100, one of a very popular benchmark for computer vision, and this is white ResNet, a very highly computationally expensive model, and this is ResNet 32, which is not so expensive, and actually it's much more efficient than this one. And these are the results that we obtain in terms of accuracy for if we train independently net 1, white ResNet, and net 2. Okay, so these are the results. What happened if we use this information, the information of white ResNet, and we distill the knowledge of the white ResNet to the ResNet 32? What happens is that we get some increment in the accuracy 0.5 by doing almost nothing. So this cross entropy loss, so this distillation loss is very easy to compute. We are not doing anything special, and you get a 0.5 more performance on image on Cypher 100. That is not super significant, but in many cases it could be much more significant. But if you apply, instead of this, you apply co-distillation, which is this idea that I mentioned, that the both networks are learning together and there's no notion of teacher and student. What we can see is that we can improve a little bit the performance for the bigger network. Okay, that's something that it was not really expected, but you can also increase by a lot the performance of the smaller network, even much more than in the case where just you were using a standard distillation. Okay, so general idea, I'm just finishing, I have 3 minutes left. So network compression, we can start with an overparameterized model and reduce the number of parameters without losing model accuracy. The most popular approaches, network pruning and knowledge distillation. These are usually approaches that are complementary to all the things that we have talked before. So you can get any network, apply network compression, even if you have obtained this network from manual architecture engineering or architecture search or whatever you can imagine. The only problem is that given that you're starting from an overparameterized model, you are always bounded, so your final accuracy will be always bounded by the performance of this overparameterized model. So you will not do better than this. So you have to start from a model that is already good. Okay, so I have to skip like all this part, which is actually what so part of my work. So I'm skipping my work, and I'm gonna just go in directly to the summary. And so I hope that in this presentation you have understood why it's important to, in deep learning, the notion of efficiency, not only accuracy. So if you start working on deep learning, or you are working on deep learning, please stop just focusing on accuracy and start focusing also on efficiency, which I think is something very important. And actually, it's a very hot topic in the community. So if you want to work with that, go ahead. I presented you many different approaches, and there are many out there that you can also explore. And in practice, usually there is no thumb-up rule. So the optimal approach is highly dependent on the needs and the applications and the computational power that you have available. And also, you can combine many of the approaches to even get much better results. And yeah, so thank you for your attention. That's it.
Thank you, Adrià. It's a pity that you don't have enough time to present your work, but
no, it's fine.
Next time,
yeah.
We will be better. The schedule.
Yeah.
So go ahead if you have any question for Adrià, please.
Yeah, I have a question. Adrià, don't you think it's more important to first focus on the accuracy and always after you have a good accuracy, then only starting about efficiency?
I mean, it depends on your context, right? So there are contexts where you have obviously to take into account both together. So if you want to deploy a model into a robot or into FPGA or something, a hardware with really low computational resources, you have to start from the beginning, not only focusing on accuracy. You have to start from the beginning focusing on efficiency. And the problem also is that even in these cases where, you don't care about efficiency, I think that, so I try to explain why I think we have to start stopping, so we have to start changing our mentality about that accuracy is the most important thing. And that first we have to just focus on accuracy, because it's not true. There are many cases where it's much more important efficiency. So I don't care about obtaining 0.1% more accuracy in the validation set of ImageNet. I don't really care. What I care is, for example, if I deploy this model into a device, what will be the cost of the energy in that I will have to spend on that device, and that's much more important than 0.2% more accuracy on ImageNet or whatever. So the question is so the answer probably depends on the context. I think that in many contexts, you have to take into account both things.
Okay, thank you.